I've been super busy. S- um, Chapter 6. Okay, first order of business. Thank you all for giving me wonderful comments and critiques and places where I misspoke about things. I do very much enjoy that information, and I was initially just planning on appending that to the end of whatever chapter I was on as those comments came in. But I feel like these are already kind of taking up a fair bit of time, and I don't want that to feel like it got in the way or later find something else from a chapter where I already did comments on it, and that just feels gross. So my solution is that every 5 chapters, I'm going to release a separate video that goes over all the things that I said wrong or things that didn't make sense so that you all can get more information and it's a little bit more of a polished experience. Second order of business, enums and pattern matching. So this is the second time I've recorded this, and I think the first time I was a little bit jaded. I had a hard time with this chapter when I didn't think I would. It's not a particularly long chapter, but I got like really turned around in a lot of places, and it was a little bit frustrating because I feel like I understood what enums were, and the more I was going through this, the more like pressure I felt to understand it thoroughly, and then I just got like too particular and pedantic in the way that I was reading through things. So hopefully that doesn't come across this way, but I will make some statements about how I think maybe this could be structured in a slightly better way, because it really only threw me for a loop in a couple small spots, but it kind of exacerbated that underlying like nervousness to get things right. The enums are initially defined as some sort of option for, different things. And I really like one particular example they used at the end of this chapter, but I feel like it's going to be silly if I bring that up first and then talk about it later. So it starts off by saying IP addresses, and we know that you can only have one of 2 different types of IP addresses, v4 or v6. So an enum makes perfect sense in this case. But then it says, well, let's say we wanted to have extra information stored about these, IP addresses, and we wanted to use an enum in this process. It goes on this kind of little tangent about how you could do this if this, ability didn't exist. And I think that makes sense, but it kind of just confused me because I was like really trying to understand how enums would work, and then to be told this was later just kind of felt like, well, why did you do that? And I think it was just because I was having a snotty, bratty kind of day. But immediately after, it says, if we wanted to store v4 addresses as 4 U8 values, but still express v6 addresses as 1 string value, we wouldn't be able to do so with a struct. And I read this as, you wouldn't be able to, I cannot do it as a struct. And naturally, I went and I tried that out, and I could. So it was like, well, why did you lie to me? But what it's saying is that doesn't make any logical sense, because if we define a struct in the same way as we would define an enum with v4 or v6 in this, let's say this way, I can't specify one or the other with these 2 different fields. I would have to define this struct IP address with a v4 and a v6 and give some garbage value for one or the other depending upon which I chose, which is why enums are useful. And I definitely read this first section where it says, currently 2 major standards are used for IP addresses, version 4 and version 6. These are the only possibilities for an IP address that our program will come across. We can enumerate all possible values, which is where enumeration gets its name. That is very obvious that they're not saying that you're not able to do it with a struct explicitly in the code or syntactically, but that no longer makes sense because we then would have to define garbage values for this particular kind of struct. And then to make it a little bit more confusing, on this next page, also, congratulations, 100, woo! It talks about messages, and it has this enumerable to define the types of messages we will receive. And when I first read this, I got confused and I thought that, quit, move, write, and change color were like the states of messages, and they could potentially change for the same idea of a message. And that's very wrong. And hopefully I'm not the only one who got a little confused here, because I'm a little embarrassed. But what this is saying is, when we have an enum message, we have a quit message, a move message, a write message, and a change color message. And those are the 4 messages we would expect to see. Not that there is this idea of a message and it will transition between different types of things over time. And that makes sense. And when it goes on to talk about why this is useful, because we can define a method for an enumerable, and that means we wouldn't have to define 4 functions. One that takes a quit message, one that takes a move message, one that takes a write message, and one that takes a change color message. We simply can write one function that would handle all of those messages. It was confusing because I was still thinking about these types. So hopefully that clears it up for any of you guys that also got confused in this way. But yeah, it was only downhill from here. It then talks about options and why they're useful, because it relegates a none state to another corner of where we need to be putting our focus while we're programming. But I was still like, wait, I don't understand enums. Why are you telling me about a specific one? And we'll go to this towards the end, but I do want to get to the good example of an enum in case it really hasn't hit home yet. Coins. I found coins for this exact purpose. If you have a coin, it can be one of the following, let's say, but it can't be a coin that is in the state of quarter and then moves to the state of penny. I'm simply saying I have a coin, it is a quarter, or I have a coin, it is a penny. That's it. So when this example came, I was like, okay, this is where I thought I was from the beginning. And then I had to reread it all, and I was like, oh man, okay, salty boy. But then they use this example of an enumeration to show how we can use a match and essentially define control flow around what particular type an enumeration is. In this case, we have value of cents as a coin, which will return a U8, and it's going to match any number of these coins, penny, nickel, dime, and quarter, and return a value 1, 5, 10, or 25. And I initially wrote, hey, does this need to be exhaustive? And immediately after, it tells us matches are exhaustive. And then it says, if we don't handle a case, it causes a bug and it'll throw an error when you try to compile it. So I like that when I ask a question and the book's like, bro, just chill out. You'll get your answer in a second. The other thing that's nice about these matches is it doesn't need to be simply that it just returns a value whenever it happens. We're really just defining what the code's going to do when this match takes place. So in the previous example, if we append to the penny case, hey, we want to print out lucky penny and then still return it, that's perfectly valid and we can do so. And since enums can contain other enums, here we have an example where a quarter has a extra field US state, which is an enum with all these different variants. Well, when we're talking about when we match that case, we need to consider what this field has in it. So if I look at this quarter, it says we have a state and we want to print out, here's that particular variant. This was a little bit weird, and you can tell from my comment here, I wasn't sure whether or not that variant that's being called state here is a string, but that only is possible when we're deriving debug, which it says right here. But it also threw me off because it ends up talking about this state, and it makes sense from this example being drawn out in this way. But I try to think about code as like, I'm given a bunch of code and I need to understand it. Not I'm like starting from nothing and working towards it, because I find myself in a situation, even with stuff that I write, being in the weeds of like, what was I thinking when I wrote this, and not being able to discern stuff. This goes back to my named parameter thing that I said in a previous episode, but I was particularly confused because let's say this wasn't as clear of an example and we had some enumeration match and we don't know what the state is. Like, what is it? Well, I can assume based upon what's down here what it is and how it will function, but I don't get that type information immediately just from seeing this code. And I pause and I take a deep breath and I realize, well, it's statically typed. So what I should do in this situation, rather than getting confused, is pause and say, I'm wondering what this quarter is. Okay, well, what is it defined as? Okay, well, what is this defined as? okay, I got it, right? It doesn't take that much time, but the idea that I'm down in this code and I have to like move around is enough of like a cognitive load on the way that I try to think about things that I'm probably going to have to think about some way to leverage like a plugin inside of Vim to make this a little bit clearer as I'm typing stuff out. Okay, so then we talk about matching with option, and this was the spot that I skipped over initially, but I do want to talk about this because I think it's interesting. Option is a way that Rust can relegate all of the like null, none, nil, Schrodinger's variable possibilities into a corner that you handle when it shows up, and the rest of the time you never have to worry about none. So in the runtime environment of Python, I don't know how often it has to do a check at any point that anything is not none, and then, you know, say this doesn't make sense, there's nothing here, I can't do anything. We don't have to do that in Rust. It's kind of just expected of you to handle those cases as they arrive, and those cases are called options. So in this case, it just shows this let some number equal sum 5, and let some number equal sum a string, and let absent number equal specifically the type, none, and whatever some number, some string, and absent number are actually options. They're the option type. You are given an option back. You're not given the thing that's in a potential state. You're given an enumerable, and you have to match against it. So we specifically know in this case, if I get an option back, I need to check whether or not it's none. And once I've done that, well, then I know it's not none, and I can continue going. Or if it is none, I know how to move forward with that example. And I think that's actually pretty clever, because it means that you have to think about what could potentially fail exactly when it happens. And then the rest of the time, you don't run into any of those weird issues because you've already handled it when it can specifically happen. So going on to matching with option, we can potentially take something that expects an option or returns an option, so long as we match all the potential enumerations that option can have, and in this case, none or some. And that way we can, I guess, continue moving forward with our, is this thing in a known state or an unknown state, and how do we handle it by providing these kind of functions? Or at the time we have that particular option, we just break out of it by simply saying unwrap, accept, etc. And in the case where we have an exhaustive list that we're trying to match against, but we don't care about some values, we have the underscore placeholder. So in this case, we have some thing that gets passed into this, and we want to match if the value is 1, 3, 5, 7, but everything else we don't particularly care. Well, we can provide that underscore and then give it these open parens, and it knows, okay, well, in this case, this match is exhaustive. I will always match to this if I don't match anything else before that. And boy, oh boy, this might sound like I only want to match one thing and everything else I don't care about, and they figured that's probably going to be a common enough pattern that we need to include some extra syntax to make that easy. But I don't like it. This if let doesn't make sense to me. So I'm going to say it the way that I think it works and the way that I understand it to work. We are going to match on sum8 value. And if this sum8 value equals sum3, then print line. And we can also add an else to the end of this and do some other stuff too. If let sum3 equals sum8 value does not mean to me this is a match. It's not equivalent. And if let doesn't inform me that it's a match. So it's just like, wait, what? So I think I understand it now, and I'm sure in time I'll be like, well, obviously this is super clear. But at the time I read this, it's like, I don't, what? And the last thing I want to just point out before we jump into the code is this 0u8 that shows up in a couple spots here. I didn't see this defined anywhere, but what this is saying is I'm giving you the value 0, and it's an unsigned 8-bit integer. Don't let the type be automatically assumed by the compiler. I'm defining it explicitly as a U8. And so if I wanted to do 300 I16, well, instead of it defaulting to I32, well, now we know it's I16. So that just shows up, and if you thought it was an O because of the font, you're not the only one, so hopefully that's clear. But that's the end of this chapter. In spite of being relatively short, I managed to make it really long, and let's actually go to the terminal and try to make sure we fully understand all these things before we go any further. Okay, so in this first example here, we have this struct IP address struct. And this is just to show initially when it was like you can't define a struct with v4 being 4 U8 values and v6 being this. It's like, well, I can, but it doesn't mean that it makes sense. So if I actually was to go to any spot that this IP struct was defined, I'd have to define an IP address that has 2 IP addresses in it, or to go back to our coin analogy, a coin that is a penny and also a quarter, or a coin that somehow has both. It doesn't make a lot of sense. So we're gonna throw that idea away, but we're going to also expand upon where that got confusing and why that doesn't make sense by simply just talking about what an IP address is. And it's a number. It's an ID for a computer. It's a way to address it. And so I figured I would write my own IPv4 struct, and then I could have an enumerable to like select it and show the various types that this IP could be. So I have this from string method where I'm actually splitting apart this IP based on this dot, and then I'm essentially adding these as an integer to get a decimal value for it. And that way we get the stringy way of looking at an IPv4 address, and we have an actual numeric value defined to it. But in this new function, I have 4 octets defined in the way that the book kind of defined it and the way that that initial struct defined it, where it essentially I need to take these and create a string with all of these dots in between them, and then I need to take all these octets and kind of like push them together based upon their value as that octet inside that number. So hopefully this will be relatively clear when I run it, but it looked really ugly to me, and I reached out to my friend Stu, and he told me that this probably wasn't the best way to define it. So what I actually did was I learned that you don't need to do any of this. We have this wonderful format macro where I can provide it a string with the curly braces just like I do with a print, and then provide it any number of these values and it'll work. So that's actually really cool. This pipe equals operator here is actually a bit shift left, which will take some sort of value and move it over however many number of bits. So I initially take this first octet and move it over 24, and I move the second one 16, and I move the next one 8. Well, we'll see. I swear we're gonna run this code. The last thing that I wanted to show was how this for loop and these bitwise shifts are the same thing, but what I would like to know how to do in the future is to just say for octet in, I guess, args, a way that I can get 01, 02, 03, and 04 as some sort of iterator. If that's possible, then I'm going to use that a bunch. And I guess the last bit here is these IPv4s are returned in the from string or new. And so eventually I can invoke these in this way, where I have a new from the octet split way, or I have it in the from string in this way. And I also wanted to be able to print out these. So just to show how they actually look, they're all the same thing, but I didn't know how to do that initially. So I made this method called printer where I just do multiple print lines. But then I figured if there's one thing that I'm going to cheat and read ahead, or, just Google to find out, it's how to actually implement the display trait on some particular type, because I'm going to be using that a lot, and well, I think it makes this easier. So this printer is doing the same thing as this display trait. So whenever we call print on an IPv4, it's going to call this display, which is why we have test.printer and now just print line here. So let's run this. Perfect. Okay, so as we can see here, we have a v4 and we have a v4, and they're both 127,001, and they both have the same decimal value, and obviously they have the same binary value. And so when we have 127 as binary, we have to shift that over so far. So this is all the 8 here, and then this 0 here is these 8, and then this 0 here is these 8, and this 1 here is this 1. And so that's actually what that shifting is doing in a binary way. But I don't actually have to print it in a super strange way to do a binary print, or I don't have to store it in a weird way, I guess I should say, to do a binary. I just have to call this print with a B at the end of it, and I'm actually just doing a padding here so that it's 32 things long. So hopefully that's clear as to what that does. It took me a little bit to actually understand it. And finally down here, we get to the point where we're actually defining this enum. I was initially using that struct from before, but we can just write this out the same way that we defined our test. And we finally defined these two functions that basically are just matches to see what we get when we pass this an enum. So since this IP adder is the enum that's defined, well, we need to check what types it can be. And I simply have if it's this v4 or an else case, then if it's a v4, I print, otherwise don't do anything. And what I thought was interesting here is this underscore needs to be used to define what we do if we don't care about the inner field values of that enumerable. Since this v4 is this IPv4 struct, if I was going to use that IPv4 struct, I'd have to define it in some sort of way here, and then I could simply just use it inside of that function call. But since we're not, it's an underscore. We can ignore it. And our final function, this print with if-let, is the exact same thing as above, but using the if-let syntax. So here we say, if the thing we're providing in X matches IPv4, then print this line. And we can also have the else down here if we cared about it, but I do not. And holy Toledo, that is the enumerables. There were a lot of things in here that maybe were outside of the context of this chapter, but I very much appreciate learning these things along the way. And as I continue to go forward, I might just make more than one file as I'm working through these chapters, because I think it'll be clearer than me commenting out things or saying, this is all the stuff that I learned and I want to now talk about it. I think it's probably better if we break it up into individual examples of how that code actually looks and runs. Well, that covers it for chapter 6. Hopefully the code examples were useful for you understanding what's actually going on. They certainly were for me. And I also just want to say that next week I'm going to continue releasing another chapter, so expect chapter 7. But in the interim, I'm going to release that addendum video, so really like a 2 for the price of 1 kind of thing. And then after chapter 10, we'll do the next one, yada, yada, yada. Thanks so much for joining me on this. Hopefully you learned something, and I'll see you in the next chapter. This pipe equals operator down here is actually a bit shit.